Welcome to another episode of Learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. And this is my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test July 2025. In this video, we discuss the solution of a problem from the section Linear Algebra, and the problem is related to the counting the subspaces of a given finite dimensional vector space and counting surjective linear transformations. Right. This question is placed in part C, which is a multiple select question. There may be more than one answer and the question carries 4.75 marks. The question ID is 562954147. This question is suitable for all these examinations. Right. The given question is, consider the field f suffix 3, f3, consisting of 3 elements. It is a finite field consisting of 3 elements. That is, f3 is under addition modulo 3 and multiplication modulo 3. Its elements are 0, 1, 2. Right. Let V be the f3 vector space of dimension 3. V is a vector space of dimension 3 over the finite field f3, and W be a vector space of dimension 2 over f3. Which of the following statements are true? We are given 4 options. Option 1. The number of two-dimensional subspaces of V is 13. We have to count them. Option 2. The number of surjective linear transformations, surjective means onto linear transformations, from V to W is 624. Again, you have to count them. Option 3. The number of one-dimensional subspace of V is 13, as in option 1. Now, option 4. The number of linear transformations from V to W is 3 power 6. Again, you have to count them. Right. Let's now discuss the solution of the problem in detail. We are given F3, a finite field with 3 elements, and FQ. In general, we talk about a finite field with Q elements. In our case, Q is equal to 3 elements, and the elements are 0, 1, 2, under addition modulo 3 and multiplication modulo 3. We are given V, a vector space over F3 of dimension 3. That is, the order of the number of elements present in V is 3 cubed, that is 27. That of W is of dimension 2 over F3. So, the order of W, the number of elements present in W is 3 square, that is 9. Let's now discuss the solutions, the options, one after the other. Right. Now, we recall the number of k-dimensional subspace of an n-dimensional vector space over a finite field FQ is given by, we are counting the number of k-dimensional subspaces of an n-dimensional vector space over a finite field FQ is a finite field with Q elements, is given by the Gaussian binomial coefficient. It is called. It is NCK suffix Q. That is the binomial Gaussian binomial coefficient, and it is given by Q power n minus 1 multiplied by Q power n minus Q multiplied by etc. Q power n minus Q power k minus 1. We are counting the number of k dimensional ones. So you have to go up to k minus 1 by q power k minus 1 into q power k minus q, etc. multiplied by q to the power of k minus q to the power of k minus 1. You have to remember this formula. And if you have not studied this formula, please remember this one. It counts the number of k-dimensional subspaces of an n-dimensional vector space over a finite field Fq is given by the Gaussian binomial coefficients nck suffix k suffix q, and it is given by q power n minus 1 multiplied by q power n minus q multiplied by q power n minus q square, etc., etc., multiplied by at the end q to the power of n minus q to the power of k minus 1 by q to the power of k minus 1 multiplied by q to the power of k minus q multiplied by q to the power of k minus q square multiplied by, etc., q to the power of k minus q to the power of k minus 1. Right. So in our case, we have to find out two-dimensional subspaces of V. The dimension of V is n, three-dimensional, that means k is 2, n is 3, q is 3. Right. We want to go to option 1. The number of two-dimensional subspaces of V is 13. The number of two-dimensional subspaces, that is k is equal to 2, of a three-dimensional vector space V, that is n is 3, over the finite field F3, q is equal to 3, is given by the binomial, the Gaussian binomial coefficient. Here n is 3, k is 2, q is equal to 3. Sorry. Now this is given by the Gaussian binomial coefficient 3c2 suffix 3. And by formula, it is 3 cube minus 1 into 3 cube minus 3, only two factors, by 3 square minus 1 into 3 square minus 3. Simplify, further simplify, we get the answer is 13. Thus, option 1 is true. Let's go to the option 3. The number of one-dimensional subspace of V is 13. Right. The number of one-dimensional subspaces, k is equal to 1, of a three-dimensional vector space V, the dimension of V is 3, therefore n is 3, over F3, q is equal to 3, is given by the Gaussian binomial coefficient. And in our case, n is equal to 3, k is equal to 1, q is equal to 3. So it is given by the Gaussian binomial coefficient 3c1 suffix 3. And one factor only, 3 cube minus 1 by 3 power 1 minus 1. By formula, right, simplify, and you get 13. Yes, option 3 is also true. Right. We continue in the next slide. Right. Option 4. The number of linear transformations from V to W is 3 power 6. How to count? Now, a linear transformation T from V to W is uniquely determined by its action on a basis of V. Let B is equal to three-dimensional vector space. Therefore, three vectors, B is equal to V, the set consisting of V1, V2, V3, be a basis of V. Now, for each basis vector Vi, its image T of Vi can be any vector of W, where W has 9 elements. So the number of choices for T of V1 is 9. The number of choices for T of V2 is 9. No conditions are there. So the number of choice for T of V3 is 9. Therefore, the total number of linear transformations will be, by product rule, 9 into 9 into 9. No conditions are there. That is why 9 into 9 into 9, that is 3 power 6. That is 729. Right. Right. So that is option 4 is true. Option 4 is true. This we will be using after in option 2. Next option. We go to the, and here we have the general formula for this. And the number of linear transformations from an n-dimensional vector space V to an m-dimensional vector space W over a field FQ is given by Q to the power of n into m. Remember this formula? Note down. Right. Right. We move to the next slide. That is the option 2. This is this counting is interesting, and you have to understand this. The number of surjective linear transformations, surjective means onto linear transformations from V to W is 624. First, let us see for surjective case. A linear transformation T from V to W is surjective, that is onto, if the image of T is the whole of W. That is, the dimension of image of T is equal to dimension of 2. Dimension of W is equal to 2. If the dimension of image of T is not 2, that means if it is less than 2, then it will be non-surjective. Now, the number of surjective linear transformations from V to W is equal to total number of linear transformations from V to W, which we have already calculated, minus the number of non-surjective linear transformations from V to W. This is what we have to find out. And this is 3 power 6. 3 power 3 into 2, that is 3 power 6, that is 729, minus the number of non-surjective linear transformations from V to W. Our concern is to find out the number of non-surjective linear transformations from V to W. A linear transformation T from V to W is non-surjective, not onto, if the dimension of image of T is less than 2. Yeah. If it is equal to 2, then it is onto. If the dimension of image of T is less than 2, then it is non-surjective. Then what are the possibilities? The possibilities are the dimension of the image of T is either 0 or 1. Let us consider the first case when its dimension of image of T is 0. Case 1. Dimension of image of T is 0. The dimension of image of T is 0 means image of T is trivial, that is 0 vector, 0 only. It is 0 space. Right. That means T sends every element of capital V to 0. So T of V is equal to 0 for all V belongs to V. What is that? It is a 0 linear transformation, a trivial linear transformation. So how many such linear transformations are there? There will be only one such linear transformation, namely that is the 0 linear transformation. Okay, keep that in mind and move to the next slide. Right. Now go to the case 2. The dimension of image of T is 1. We have considered 0. Now we are considering 1 because it is less than 2. So the image of T is, what will be the image of T? Will be a one-dimensional subspace of W. Image of T will be a subspace of W. Therefore, image of T is, the dimension of image of T is 1, means the image of T is a one-dimensional subspace of W. So how many such one-dimensional subspaces are there for W? The number of one-dimensional subspaces of W is given by the Gaussian binomial coefficient, that is 2. Dimension of W is 2. We want one-dimensional 2C1 in F3, that is suffix 3. And by formula, it will be 3 square minus 1 by 3 power 1 minus 1. That is 8 by 2, that is equal to 4. Right. In this case, n is 2, k is 1, q is equal to 3. Right. Right. Now, for each such one-dimensional subspace, we have 4. We have 4, 4, 4. Out of that, take one of them. For each such one-dimensional space, let us call it as S. We count the number of linear transformations I'm sorry, number of linear transformations from V to W whose image is exactly W. So, how many such there are? The number of one-dimensional subspace W, 4. One of them you take it. Let us say yes. We count the number of linear transformations from V to W whose image is exactly yes. The dimension of S will be one-dimensional. So, this is equivalent to counting the number of surjective linear transformations from V to S. Exactly it is going, therefore, it's surjective linear transformations you are counting from V to S. The number of linear maps from V, whose dimension is 3, to S, whose dimension is 1, is 3 power q power n into m, that is 3 power 1 into 3, that is 3 cube, that is 27. Now, out of these 27, there is one map, only the 0 map is not surjective. Out of these, only the 0 map is not surjective. Right? It's not surjective. So, we are counting surjective linear transformations, and in this, one of them is a 0 map is there in this 27, which is surjective. Not surjective. Therefore, you have to remove that one. So, 27 minus 1, that is 26 surjective maps are there from V to S. Right. And this 26, you got it for this S. But how many S you can have? 4 S's. The total number of transformations with a one-dimensional image will be the number of choices for S, that is 4. The number of one-dimensional subspaces multiplied by the number of surjective maps onto each subspace. S has to vary. So, the number of one-dimensional subspaces is 4. 4 multiplied by the total number of surjective transformations will be maps with 0-dimensional image. Yeah, this I have not completed. The number of one-dimensional subspaces is 4. The number of surjective maps onto each subspace is 26. For each S is 26, and there are 4 S's that you can count. Therefore, 4 into 26, that is 104. So, total number of surjective transformations, which we have already seen in the previous slide, maps with 0-dimensional image, that is 1, plus maps with 1-dimensional image, that is 104, 105. Right. Now, this is what we have seen in the last slide. The total number of surjective transformations is total number of linear transformations from V to W, that is 3 power 6, that is 729, minus the number of non-surjective linear transformation from V to W, that is 105. That is 3 power 3 into 2, that is 3 power 6, that is 729, minus this one, the number of non-surjective linear transformations from V to W, that is 105. So, 729 minus 105, that is 624. Yes, the number of surjective linear transformations from V to W is 624. Thus, option 2 is true. Now, which options are True? All the options are true. The answer to this question is all the options. Options 1, 2, 3 and 4. That is the detailed discussion of the solution of this problem. This problem completely relies on counting, right? And this is a combinatorial counting is involved in this example. And for some of our students, especially the students in South, these formulae, that is the Gaussian, binomial coefficient, etc., and this counting of number of linear transformations and so on and so forth is not familiar. And I made it. I have made an effort to make it clear how to count them, and especially concentrate on option 2. The counting is beautiful, and learn the counting, and I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. I earnestly request each one of you, please join as a member in my channel and support me and my channel. This is my channel. Please subscribe my channel if you have not already subscribed. Yes, I'm sure I'll be meeting all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.